Okay, so I just want to say thanks again to Samir for doing this sort of set of exercise class and sort of journal club-like thing to try and educate us all on the issues of information and black holes and so forth. And I strongly encourage everybody to do the homework problems. But the plan for the basic today is Samir's going to give an overview of what we're all here for and what we're trying to, what he's going to try and educate us about. And then by great good fortune, the first homework set, pretty much 80% coincided with stuff I had in my GR course. So I'm just going to take those slides from that GR class and take you through them, but hopefully you'll all jump in and Samir will jump in and make commentaries as I go. And then in subsequent ones, we're going to have to work a bit harder and maybe I'll hand it off to somebody else to try and lead the discussion. But for the moment, Samir, thank you. Please, would you start giving your overview?
Yeah, thanks to everybody for coming for this. Let me try to share a screen here. Let's see if that works. Okay. Okay, so can everybody see a PDF slide and also my cursor on it?
Yes.
Yes.
Okay, great. So here are just my brief overview. It's just like 8 slides, so it's nothing much for me to say here. So my own opinion is that the fuzzball paradigm has given a very satisfactory solution of the information paradox. So if you ask me, this problem is done, and therefore we should be doing what I think most of you, if not all of you, there in the audience are doing. We should focus on constructing fuzzballs, studying their properties, and then seeing how this fuzzball paradigm might address puzzles in cosmology. There's a direction forward to go from all the beautiful things we have learned about quantum gravity from fuzzballs. Just to summarize what we have learned from fuzzballs is that in the classical black hole, all the stuff goes to the center, you get a vacuum around the horizon, then you get these entangled pairs, and that leads to the information paradox. But then in string theory, you don't actually get that every time you try to make a black hole by taking bound states of branes and things like that. You actually find the size of the bound state swells up, and you actually always get something like a planet or a piece of coal, and that radiates from its surface like a normal body. So in fact, string theory is very clever and evades this information paradox. So there's none of that deep new physics that people sometimes postulate that quantum mechanics breaks down, or you get non-local wormholes going from here to there, and none of that seems to happen. String theory automatically seems to take care of itself. So you would say this problem is done, and we should be now using the main lesson we have learned from here, which is that quantum gravity doesn't act just at the Planck scale. If you have a large number of particles n, then it acts on n times the Planck scale. That's a rather interesting lesson. And so for a black hole, which has a lot of particles, it just basically grows to a macroscopic size. And then you can try to see what it means in terms of the cosmological horizon and so on, which are issues I'm interested in. So you would think, why is the field not going in that direction? Because some groups are actually looking for other solutions to the paradox where the horizon remains smooth. Smooth means just the local vacuum. And so then you will get the pair creation and you'll be back in the information paradox. So what exactly are these groups saying and why are they doing that? So I'll just call this kind of work under a rough moniker of islands. And this is my understanding of the island. Since I'm talking about other people's work, it's okay, it's possible I'm not correct about what I'm saying that they're doing. So the net output of the island proposal that I can extract from all the papers I've read over the last 1.5 years is the following. Some hitherto unknown non-local interaction takes some quantum bit from inside the black hole and deposits them far away. So when I say far away, it's not like the scale of the radius of the horizon. Let's say that's 3 kilometers for a solar-sized short-shell hole. It's the distance to where the Hawking radiation is, which is much further. So it's like, that scale is like m cubed. For lack of a better words, I'll just call that a wormhole, but you could imagine any kind of interaction. So the whole idea is there are non-local interactions that connect the inside of the black hole to things far away. So there's nothing like that with fuzzballs, and there's nothing like that I have seen in string theory. So this would sort of be a new postulate. Hopefully somebody can show how it comes from string theory, but my personal belief is that it's not there. So if they look into string theory, my belief is they won't find it. But anyway, this is what the proposal is, because if you keep the horizon smooth, then you're forced to actually have non-local effects to get the information out. So this looks quite straightforward.
Can I ask a question? Since this is CAS, you said that far away was m cubed. I mean, what's setting the scale? Why aren't you saying, say, 10m or 100m? Because the obvious scale is just m.
Yeah,
So
good question. So what happens is Hawking radiation is emitted at a certain rate. So if you're looking to see where the typical particle, how far it has gone by the time, let's say, half the black hole is gone, then that is m cube, because the scales of the black hole radiation are the following. The wavelength of the emitted quantum is the radius of the black hole. There's only one scale in the problem, the radius of the black hole. Then so that's the wavelength. From there you can find the energy. Then what's the time interval between different quanta coming out? Well, when one quantum goes out, which is the speed of light for time taken at the speed of light to cross the diameter of the black hole, then the next quantum starts. There's no other time scale in the problem. And how long does this evaporation go on? Well, if you know the mass of each quantum, you can find out what is the time till the black hole is gone. So then you can find out, if you put all this together, you find that the time over which the black hole evaporates is the Schwarzschild radius, let's say 3 kilometers. That's proportional to the m of the black hole, times m over m Planck whole square. So m cube, of course, doesn't make sense of the distance, but m over m Planck is a dimensionless number. So m over m Planck whole square times the radius of the horizon, let's say 3 kilometers. That is the actual distance to which the typical Hawking quanta goes by the time the black hole evaporates away. So that's the scale m cube, and 10m, 100m, I'll call those order m. So anything which is happening up to 4m, 6m, you can say there is something to do with the fuzzball. So anybody who says so I don't think that fuzzballs have effects going out to 100m, but if somebody were to say that, he would just be talking about a rather diffuse fuzzball. So anything happening at the scale of 10m, let's differentiate that from things happening at the scale m cube. And this proposal has to do with the fact that you can actually affect the radiation far away, collect it, do something, and influence the black hole. And that's why I'm saying this is a genuinely non-local proposal. Does that answer what you were asking?
Yes, thanks. Is there anything happening at the scale of m squared in this sort of discussion?
So I have not seen m squared. I mean, we can think about it, but I think, again, this is a good exercise for the students. They should first of all check that m cube is the time scale or distance scale at which the radiation comes out. And they should check the energy scale of the radiation, the interval between quanta, and how many quanta are emitted. You can put the numbers in for a solar mass black hole. You find some 10 to the power 77 years is the evaporation time. So that, from there at the speed of light, you can find the distance. And that's a much longer distance than, because the universe only 10 to the 11.
Let me add a footnote that this is just a straightforward calculation. You just get out Stefan Boltzmann law of Planck curve and you've got it.
That's right. Okay, so if this was the proposal, if somebody actually came and told you that the whole proposal is that you can take bits from inside the hole and put them outside, not many people might be happy with it because it looks sort of ad hoc and very non-local and so on. But the problem is that there are a lot of circular arguments in the literature, and so it's not clear to people that the new physics is really a proposal for non-local interactions, that nothing else has been added to what was earlier done except the fact of these non-local interactions. So these circular arguments actually create an impression that somehow you can get the information out in some subtle way while still keeping a semi-classical horizon without having any non-local effects. So that is the main confusion. And the goal of these sessions that we are going to have is that you can actually understand completely that this is not possible. And so you can exactly understand what is being said in different papers and where are their non-local effects, what are they actually trying to do. The papers are often very confusing. They're often also very long, but we want to be able to have the power to just look at any such paper and within an hour extract the essence of what they are saying. So in fact, the fact that you cannot actually keep a smooth horizon and also get the and no non-local effects and still get the page curve to come down is actually forbidden by the small correction theorem. So that is one thing that at some point in these sessions we would like to learn. Let's make this a little more precise as to what is the difference between what the fuzzball people do and what the island people are doing, because the small correction theorem tells you there are only two sharply distinct possibilities. There's nothing like in between. So what are these like circular arguments? Many of the circular arguments are of the following kind. If you look at what they are actually writing, they're simply modeling a piece of code. So they may look like they have lots of bits and they have system H, system E, system this, system that, but all they are doing is making more and more models for something which is a piece of code. They're not putting in ever that it actually has a smooth horizon. So they're never actually looking at the fact that a smooth horizon creates particle pairs, the original Hawking calculation, that is not there anywhere. And then, but on the other hand, it looks like they're talking about a black hole and they say we have a smooth horizon. So a large fraction of the papers, maybe 50% or more, are simply talking about pieces of code. So there is nothing there actually. And one just has to be able to understand how they're actually talking about a piece of coal, and how to notice that somebody is just talking about a piece of coal. He doesn't actually have a smooth horizon. So if he says this is the physics, he's actually talking about a fuzzball, and it's not doesn't have to say a fuzzball is a piece of coal and that's the fuzzball proposal. Okay, fuzzball is like a piece of coal is the output, but the real thing is that in string theory, one has been able to find solutions which behave like a piece of coal and don't collapse into the horizon. That is the fuzzball construction, which is a non-trivial part. But they are not doing that. They're just assuming that the black hole looks like a piece of coal, in which case they're assuming the fuzzball without actually making a fuzzball, which is a non-trivial part of the fuzzball. And they're actually not saying anything about a smooth horizon. And then at the end, you'll see them also say, aha, we have done it with a smooth horizon. So that's the kind of thing that after we are done with these sessions, you should be able to look at these papers and just pinpoint it right away.
So again, Samir, can I ask you a question?
Yes, please.
I'm actually a bit confused. Are they really saying that they don't have non-local effects? Because if this all sort of comes back to the ER equals EPR kind of discussion, that was about non-local effects, no? Like in the original Maldacena-Susskind paper, and all that is wrong.
Maldacena is very upfront and clear about it. He is talking about non-local effects, right? So Maldacena is clear about it. And so that's what I was saying up here. This is the proposal. In fact, this picture is from the Maldacena-Susskind paper. And they say this is exactly it. It's non-local effects. The confusion is that people somehow have gotten the idea that if things are just entangled over long distances, that is the only effect they need. It's not a Hamiltonian. See, a Hamiltonian is an interaction. Entanglement is just linear superposition of two states. So I can have an electron in my room, you can have an electron in your room, and they can be in the state up, down, minus, down, up, like in a singlet, but there's no Hamiltonian which is actually affecting my electron to your electron. So if I take my electron and I turn upside down in a Stern-Gerlach apparatus, it'll actually do nothing to your electron. So this is the old EPR story and so on. But what Maldacena actually needs is that when I turn my electron upside down, your electron will turn upside down. Now, a lot of people don't actually see that consciously, or maybe they do that, but that's not what they're doing in the papers. So what they
even the authors, you say, even the authors of all these like subsequent island papers, they claim that they don't have non-locality, or they just don't address it and are silent about it.
Right. So that's exactly the kind of confusion we want to clarify. So when you go back into those papers, you will find either that they don't actually have a smooth horizon. They will just write some partition function, but that partition function they write could equally well be for a piece of coal, because where have they used the fact that the horizon is a vacuum? So if you don't use that, it could equally well apply to a piece of coal. So a lot of those papers are just StatMech papers. They're just saying, if you take a system, you write a density matrix, you do this, you do a saddle point. Hey, but if you never had a smooth horizon, of course that answer had to come because true for a piece of coal. So we have to go and locate that, right? So that's exactly what I was saying. That's how it comes. And Maldacena knows what he's doing because he's asking for non-local effects. I disagree that they are there, but at least he's self-consistent and he's very honest and upfront about it. But many other people are just confused. That's all.
Isn't it even a bit worse in that when they use all these SYK models, like all these lower dimensional models and so on, where there isn't even an Einstein gravity dual, that it's even worse when they talk about wormholes, like what is it even? Because they don't have a geometric concept of that in those situations. Why do you use like these SYK models to talk about?
I'd kind of like to jump in here just to say, Samir's giving sort of broad outline. I think we might run the risk of losing a lot of people if we start a technical discussion about where we're going to be in about 3 weeks now. So you know, it's fine, Andrea. It's great. I
just wanted to put it in the context when Samir says that they are claiming these things, and I just wanted to put it in the context like.
Thanks. This is really very useful, because this is exactly what I wanted to say, and that's very useful because what I was trying to do in these couple of slides was to exactly bring out the difference between what the fuzzball people are saying and what the island people are saying. Those are two opposite things, but the difficulty is this third thing where people are just confused and going in circles. So we have 3 things to understand: the fuzzballs, the islands, which are non-local, and then the confusions, and it's the confusions which are actually causing the problem. So actually, I'm very happy for the discussion. Thank you for that question, because we really want to understand these confusions. And so that's exactly what I was saying down here at the end of the slide. I mean, the SYK, I try to read about it, but exactly as you say, because everything is ill-defined, you have higher spins, it's not clear you get a good space-time, I can't see a horizon, so I can't use that as a model for the black hole. It might equally well be a fuzzball. So then, because you can't define space smoothly, maybe it is a fuzzball if they don't have a smooth horizon. What are you saying anyway? You've actually solved the problem with the full string theory. If you're only going to get a fuzzball from a SYK model, it's not interesting because we've done it in the full string theory already. Right? So who wants the toy model? Okay, so as I said, many people are just modeling a piece of coal, but this is the difference that we need to keep in mind, that the way I define a fuzzball is that there is no region around the surface where the local vacuum, which is called zero, like the vacuum in this room, the actual state there has almost no overlap with the vacuum. Okay, everything will have some overlap with something, so I call it epsilon, but epsilon is much less than 1. It's not a vacuum, as compared to the normal black hole, where the state around the horizon is the local vacuum to a good accuracy. You always have to put the epsilon because there can be some small quantum gravity effects. We are always going to allow that, but this is the actual difference between the two starting points. So in the case of the fuzzball, there is no pair production. We'll see later that pair production is entangled. A toy model for that you can say is like 0, 0 plus 1, 1 or something. So it just evaporates like a piece of burning coal. It's like any piece of coal. There's nothing like pair production. While for this, once you have a smooth horizon, Hawking's calculation shows, and that's something we'll review in these sessions, the actual Hawking calculation, that you have no choice but to get these entangled pairs. And of course, there can always be some small corrections, but then the small correction theorem tells you that the corrections don't help, and you'll be back to Hawking's answer. So then you have to do all these things that Maldacena is actually doing, that even if you're doing ADS CFT, then some part of the interior of the ADS is not actually captured by the CFT. With fuzzballs, it is captured. I mean, everything you do in the boundary CFT is some complicated state of the interior. You know, the gas, I mean, a hot gas is a particular state. A fuzzball is just a more complicated state, but the CFT captures everything. But here the idea is no, whatever is inside the horizon is actually captured by some ER equals EPR way with these radiation quanta far away. But then the important point of that is that if you manipulate the radiation quanta in some complicated way, you can actually affect the quanta in here. And that's the non-local effect we were talking about. And that's again the scale MQ. So the difference between these two, in any paper that you come across, the first thing you have to do, and we'll try to work through a lot of, I'll try to refer you to a lot of papers, and it will be a good exercise. We take a paper and see, let's say over this, whether you can just sit down for an hour by yourself and see where are they deciding which of these they are doing. And if they are doing the first one, of course, then they're just talking about a piece of coal. If they're doing the second one, then how did they get out of the fact that the entangled pairs are being created? Where are the non-local effects? So if you breeze through any paper, there are some points we'll figure out. You should find this A, B, C, D, and you can categorize the paper either into piece of coal or into non-local effects or into circular arguments. Okay, so that's the kind of thing we want to learn. Okay, so I'll just say a little bit about the problems for this week, so you can actually get some interest in doing these. So in classical physics, you know that you can have the Rindler horizon, and that just looks like the near horizon geometry of a black hole. That's problems 1 and 2. And so in Rindler space, you know, it's just this quadrant and there's nothing at the horizon. So you can smoothly go to all of it. And in a large black hole also that, you know, this region looks like Rindler. So that's problems 1 and 2. But the whole lesson from the fuzzball paradigm has been that everything we learned from Rindler space and we tried to carry over to the black hole was a mistake. And the reason it was a mistake is that the Rindler space corresponds to mass equal to 0 because that's empty Minkowski space. There is no mass. But if you're going to go to the limit of a large black hole, that's the opposite limit. It's m going to infinity. And so far, we didn't actually know why that should make a difference. But in fact, what we have learned from the whole fuzzball game, that when the mass is so large, then you have a large number of these fuzzball states. And then, you know, you can have tunneling into these states, the whole vacuum wave function gets corrupted. And it doesn't matter how big you make m, you get more and more of these. So this decoupling never works. You can't actually go near a horizon and say, now I'm like in Rindler space, because the number of states which are bothering you or upsetting your limit are also correspondingly increasing. So I think this is one of the main things we have learned from the fuzzball paradigm. But then problems 1 and 2 will show you the classical physics, and one should thoroughly understand that to be able to understand how the thing changed when we actually came to fuzzball physics. The problems 3, 4, 5, 6, 7, they are all basically taking you through the black hole in different coordinates. But that's not just to harass you and waste your time. There's a very important lesson we want to get out of this. And the lesson is that inside a horizon, there is an infinite amount of space. Now, normally that is not obvious, because if I give you a surface of radius 3 kilometers, you would think there's roughly 3 kilometers or 5 kilometers of space in there. But inside a horizon, space and time interchange roles. And because of that, there's actually an infinite amount of space inside the horizon. It is time which is limited. So you only have 3 kilometers of time, but the space is infinite. And on the space, you can actually have particles of both positive and negative energy. So we'll have to understand what those particles are. In later lectures, you'll have to go, and later assignments, you'll have to figure out how to write a positive and a negative energy particle, how you can see there are an infinite number of them, because the whole root of the information paradox is actually right there. if you did not actually have infinite space on which you can put an infinite number of positive and negative energy particles, so they net have no energy, you wouldn't have all this problem of being able to put a divergent amount of states inside the horizon. And that is just a way of restating the information paradox. So then why are we going through so many different coordinates? The short shell coordinates work only outside, so they can't tell you what's happening inside the black hole. The Kruskal coordinates can show you the full diagram, but in them, the metric does not look time independent outside the horizon. So you sort of lose the intuition that the black hole, at least from outside, is just sitting there without change from time to time. So it's the Eddington-Finkelstein coordinates that people are not usually that familiar with, which actually somehow turn out to be the most useful to understand the information paradox, because the metric coefficients, well, at least if you look at the metric outside, it's time independent, and they do cover the outside and the inside. So we'll be using them quite a few times. And so that's why you have some exercises in doing that. And so that's why these things are important. And then the last three problems, they talk about the following very important thing: the fact that the entire geometry, which is produced by a black hole will start from a star and collapses and so on, start from weakly coupled space with a star, collapses, makes a black hole, and the black hole evaporates. The entire process can be studied using these good slices, which are gently curved everywhere, and there's no high curvature anywhere. So this is crucial to understanding the information paradox, because again, many people here go in circles. They say, I believe the black hole will do this and this. I don't believe the black hole is given by the normal semi-classical diagram. So I'm done. Now listen to my theory. But they're not actually addressing the real question. The real question is, how do you make the modification here that you're looking for? Of course, you have to separately go and show that you get that modification from string theory. But even if you are postulating a modification, how do you postulate a modification to the physics in a black hole without actually getting a big modification also to the physics of our galaxy? Because in our galaxy, you can slice it with slices which are all gently curved, and we see the physics around us is just described by semi-classical physics. So how do you modify it in the black hole and not modify it here? And so this you will see coming up in many circular arguments, where people say, if the slice in the interior is very long, I will say at some point it's too long and the physics changes. Well, then you have to go to other situations where the slice is also long, like you look at cosmology, where a marble-sized universe has stretched and become as big as our universe today, and nothing has gone wrong. So you have to understand what's the good slicing of the black hole and what's the good slicing in the galaxy. So any change you make over there, you have to first check the fact that you're not screwing up physics in the everyday world. Okay, so that's it. So this is the last thing that I wanted to put up here. So what we planned to do was, one should do a large number of simple computations with particle creation in curved space to get a good feeling for how the entangled pairs come out of the vacuum. So that's what we'll start from the next homework set onwards. And we have to see what is the entanglement, how do you get the pairs, what can you do to not get the pairs, who is entangled with who. That's what we actually want to understand. Okay? The most important thing is that you have to puzzle out the answer to the questions yourself. If you ask somebody for an answer, this is what I found. If students ask me a question, if I give them an answer, they actually haven't gained anything from that, because somebody else gives them a different answer. They say, okay, that looks fine too. So then you're exactly back where you started. And what I would like to do is, if anybody asks me a question, I'd like to break it down into further smaller questions and throw it back at you. And when you actually work out those smaller things, you will actually get the intuition, after which you can yourself actually figure out your own solution to the information paradox. So we'll break it down into small pieces, and the goal is to actually make you an expert so they can open up any paper and figure out what they are saying and whether they are correct or incorrect. Okay? So that's why we'll actually have problem sets each week. But what I would encourage students to do is that you should ask more questions of your own and answer them. For example, when I was making the problem number 1, I was initially asking about all the 4 quadrants of rindler space, put the rindler coordinates, but that's too much work. Like, I can't have everybody do 40 problems a week. But if you have time, yes, you should go ahead and make coordinates in all the 4 quadrants. You should ask yourself other questions and answer them, like what points in the space correspond to 1 Planck length from the horizon. Okay, so building intuition with these very, very simple things, when enough of those intuitions pile up, that's when you become an expert in the information paradox, and that's all we'd like to do. So again, to emphasize, if you ask me a question, don't get frustrated if I just break it into small pieces and throw it back at you, because that's the only way that one can actually get intuition about the information paradox, but that's what I would like to do. So today, Nick Wander has kindly agreed to present solutions. In the future problem sets, there won't be solutions, but I'll give you places where, in various reviews and so on, where the answers can be found in almost all cases. So I'll now turn it over to Nick, and he can present these beautiful slides where he has solutions. And maybe at the end, I can come and say a little bit about the next problem set, which I'll send to Nick in the evening today, and then he can post that. Okay, so thanks. So shall I just stop share here?
Yes, that's great. And I'll share screen. So I had the great good fortune where I saw Samir's slides to realize that everything, or most of the problems were basically addressed on a graduate course I just finished in my in general relativity theory. So with apologies, I just cut and paste slides. So some of them will be a little, maybe won't quite fit Samir's problems, but basically I want to lead you through that. And maybe I'll try and ask for volunteers for the next homework set to maybe answer, maybe 4 volunteers to cover, a couple of questions each, or at least lead the discussion. You don't have to provide full answers, but it would be nice if we had the students giving, or at least leading the discussion in various aspects, and it's perfectly fine to say, I didn't understand how to do this, but this is what I tried. That would be great. So, and also, Samir, don't feel, if you feel, I might screw something up, or, or maybe you want to make some expanded comment on it. So please, as I go, do not feel shy about jumping in. And the students should certainly not feel shy about jumping in and asking questions. As I say, this is drawn from a starting graduate class, and so fairly, but it moved fairly quickly. And so I'm going to start at a fairly rudimentary level. So basically, what we're talking about is the Schwarzschild metric and in all its glory. And the basic point about the rindler system, which is, I'm taking a slightly different tack from Samir's because that's what I had in my slide, is when it's interested in what is happening in RS2M, the spheres will just go along for the ride. So really, it's this part of the metric we care about. So the first thing you can do is you can do an expansion near the horizon. You take some, and it turns out to resolve the seeming singularity in the radial coordinate, you do a standard square root branch cut. And if you do that, you get this form of the metric near the horizon. And this is what we typically think of as, in fact, the rindler system. So I've got this backwards from Samir's homework, because the way that Samir starts in the homework is simply to say, start with basically a Lorentzian metric, which are called dp and dq, make this transformation. P is equal to cosh and Q is equal to sinh. It's a uniformly accelerated frame, the rindler frame. And then what happens is that this Minkowski metric transforms back into the radial and time part of the Schwarzschild metric. But essentially what you should understand is that a uniformly accelerated observer in Minkowski space sees something that looks like this or like this in precisely the near horizon region of a black hole. And you can understand that sort of in the following sense. If you're very, very close to the black hole, if x is small, then basically what's happening is that you are in a uniformly accelerated frame, and the uniform acceleration is roughly, in some units, 1/4m. And you're basically, if you want to hover at a fixed distance, you have to be uniformly accelerated as you first learned in Newtonian mechanics. And so, but the point is that this coordinate change involves a cosh and has certain signs and inequalities. And so the rindler uniformly accelerated observer sees only this rindler wedge. The metric is flat in PQ space, but in X and T space, it is really only this side wedge that you get to see. And you can, of course, continue by mucking around with various signs in here.
Next question.
Yeah.
How do you see that the acceleration is uniform?
Sorry?
The acceleration
oh yeah.
Uniform?
So what you can do is you can take somebody who's, let me see if I get this the right way around. The Minkowski space is P and Q. So what you do is you take somebody, I think at fixed, let's see, the way you see it, you take these trajectories. So I'm trying to see if I get the right way around. Yes, you think of these as trajectories. Let's go over here. Look at these trajectories in the PQ space, parameterized by t. You calculate the proper velocity by differentiating with respect to t, and then normalizing it appropriately using the proper time. And then you calculate the proper acceleration. And you will find that the proper acceleration is a constant, which I think is 1/4m.
Oh, I see, because you get two derivatives on cosh and sinh.
Exactly. So you get so you get the proper acceleration maybe, and I think you get a 4m back from normalizing it to the proper velocity. But the calculation is simply you look at the trajectory at fixed x, and then you see that these hyperboloids, and you ask what's the proper velocity and then the proper acceleration, and that becomes the constant. If you want more homework exercises, this was homework 1 or part of homework 1 in my GR course. It's also homework 2. But that's the simple answer. It is a uniformly accelerated observer. And it really is, it really is the general relativistic version of, standing on the surface of a large planet. You feel uniform acceleration called g. Well, if you're very close to a black hole where x is not seeing much more detail, x is small, that's what you see, and that's what the observers see, and this is the exterior patch of the black hole. Any other questions, students? So I think I've answered sort of 1 and 2 of Samir's homework. Any concerns? Seriously, this is meant to be a class, so you should jump in if you've got, this is not familiar. I will put these slides on the website also, where we put the homework assignments. So once I'm done. Comments on it? Do you have any comments, Samir? Are you happy? Anything you want to say in addition?
No, I think that's absolutely great. I think the students, as I was saying, should like make their own problems around this and do them, and like checking the fact that the acceleration mu gives a constant for a trajectory of constant rindler position is actually a great exercise, because it teaches you something just about rindler also, and how the acceleration increases as you get closer. And yeah, so absolutely people should go ahead and do that.
Right. Okay. So what we're going to do, oh no, I just want to point, so this comes from my class. I want to point out that r equals 2m in the usual sort of Schwarzschild metric, of course, looks like there's something weird and singular going on there. But the stress is here that this metric, or this metric at the horizon region, is beautifully, perfectly smooth in all directions. And so as a result, you realize that r equals 2m, which is x is 0, is simply a coordinate singularity, and you've got some crappy coordinates. The other thing it also tells you is that because you have a square root branch cut in defining x, you really have, if you try and take this literally, a natural continuation, which is a double cover of your original exterior space. There are 2 branches, and this neck is really a part of a Riemann surface where you double sheet. And we're going to talk about these regions in a minute. So the basic problem is that we need to complete the geodesics in every possible direction. And this picture gives you a clue as to what you should first do. And the first thing you do is we're going to talk about the Eddington-Finkelstein coordinates, where you follow photons across this direction. Then we'll talk about following photons in this direction. So standard way you got Eddington-Finkelstein coordinates is you think about a shell of infalling photons. And that means you're going to follow a radial null geodesic. And the notation here is a throwback to some stuff I talked about in my class. But basically, the equation for geodesics is there's a conserved energy, and there's an effective one-dimensional problem, and so forth with the potential. You don't need to worry about it. The equation you really need is this, that an infalling shell of photons satisfies this condition. And that condition is really given by saying I don't have any angular motion, d theta, d lambda, d phi, d lambda is 0. And I'm going to set this to 0, and that gives you this equation. You can think of it in terms of the more general geodesic problem where you've got no angular momentum, and epsilon is the null geodesic, so these are 0 and there's no angular momentum, so the effective potential goes away. However you want to slice it, a radial null geodesic satisfies an extremely simple equation. And you write it in terms of the orbital shape, dt is a function of r, and then it's an elementary integral, which gives you the t is plus or minus this r minus r naught, and then the so-called tortoise coordinate, which is sort of 2m log r over 2m. And the minus sign for this inflow corresponds to shells of infalling geodesics. So we want to follow light into the black hole. I've never tried it, but it might be fun to try following particles in. You'll get some ghastly coordinates, but it'll probably be morally the same thing. But anyway, the goal is to follow something and see whether they get a smooth experience at the horizon. So in this equation, the integration constant labels the particular shell you're on, one of these shells. And so Eddington-Finkelstein, I don't know who did it first, there seems to be some huge gap between the 2 papers, but you choose this initial surface as your new coordinate. So in other words, you define coordinate u, which is basically this r naught, and then the surfaces of constant u are then the shells of infalling photons. And so this is your new coordinate. It follows the shell going in. And you use it to replace the bad coordinate, and there are reasons why we can talk about why it's bad, and I'm sure when we talk about the quantum system, this is going to come back. T is emphatically the bad coordinate here. And this is the Eddington-Finkelstein coordinate. So you calculate the differential of this, which is actually circular. You already know the differential of u, going back to the equation, and then you calculate what dt squared is, and you replace it in the metric. And so this Schwarzschild metric, when you replace it with the dt squared, it takes on this form. And the term to watch is this. It looks like you haven't got rid of the problem because it looks a priori like you still have some metric coefficient vanishing at r equals 2m, and therefore perhaps the inverse metric is bad. But this is the term that saves you. The Eddington-Finkelstein coordinates are smooth precisely because of this. And it's perfectly regular because if you think about the u-r directions in the metric, and you write it as a matrix, then this quantity here is, simply, I'm ignoring the spheres. Basically, this is what you get. And you realize that this matrix has a beautiful smooth inverse because there's a 1 here and there's a 1 here. So therefore, the matrix is smooth and everything is fine for 0 is less than r is less than infinity, and u going from minus infinity to plus infinity. And also notice that the metric is completely independent of u. So u is now a new killing time coordinate that you can use to study this thing. It is a null killing time, but it is still, the metric is entirely u independent. And this was, in fact, the insight that Hawking had when he started calculating, or first calculating Hawking radiation. The t coordinate is bad because it's terribly singular at the horizon. And the u coordinate is good because it just goes smoothly across the horizon. So when you define a quantum mechanical vacuum, you are making a huge mistake using t, and the correct thing to do is to use u because it's smooth at the horizon. That was the insight that he had. So Eddington-Finkelstein, the metric is beautifully smooth across the horizon, and it's done by following light shells. So I think I've done the next homework exercise. Questions or comments? Concerns? Everybody's being incredibly quiet. My graduate students I'd be beating them up at this point. Anybody? Comments? Nobody's courageous enough to come out and say something.
Thank you, that was great.
Okay, thank you. Okay, Samir, do you want to add anything to this, or are we going?
No, I think this is perfect. This is exactly what I wanted people to get familiar with. I don't actually know how many people are very familiar with Eddington-Finkelstein. Mostly people have heard about Kruskal, but right. Is this something that people use? Has this person work that people do in other parts of string theory?
I don't know, to be honest.
Nick?
Go ahead, Bogdan. Yeah.
One thing that some people might be interested to know is that, there is a choice of sign when you're doing the no geodesics. So there is the ingoing and outgoing.
Yeah, we're going to, Bogdan, I'm about to do that. I'm about to exactly that.
Okay, sorry.
So no, but if you're going to go there, I'm going to talk about it. I'm going to talk about outgoing now in a minute. But is that where you were going?
Yeah, I just wanted to say that in case you weren't planning on saying anything.
Yeah, no, I'm going to.
It's good for people to know. Yeah, okay.
Yeah, no, so if I haven't answered your question or made your comment for you in the next 5 minutes, jump in. So as Bogdan was observing, I deliberately in this particular setup considered only infalling guys, and I chose the particular sign here that gave me this coordinate. So the other thing is there are Eddington-Finkelstein outgoing coordinates. Where'd it go? So you do the same thing. You basically follow geodesics going out, and you usually call this V, or U and V tend to get inverted, but there's now a change of sign overall. And so V as a constant is going to be a shell of outgoing photons. And once again, you do exactly the same exercise, and you replace the bad t coordinate with the good new coordinate V. And basically the same thing, you get a differential, you shove it in the sort of metric, and you get a slightly, but only slightly different Eddington-Finkelstein metric. There's a sign change here, and that's the only difference. And everything else I've said is true about this thing. So we got the ingoing and the outgoing guys, and the only difference is the exchange of u with minus v, and the minus is important. We'll get to that in a minute. So these coordinates are just as good as the other ones. So you can do it ingoing or outgoing as you wish, and the u and the exchange with minus v. So what that really means, if you are dissected, and maybe this is a good exercise, is that one of these, since you're following shells outwards versus following shells inwards, it turns out that you can think of the ingoing Eddington-Finkelstein as continuing the photons into the infinite future, whereas V, the outgoing guys, continues into the infinite past. And that's why that sign is critical to the discussion. It's really about looking at the continuation of geodesics into the past. Bogdan, go for it if you haven't said something you wanted to say.
That's so, I don't have anything more to add.
Okay. Any other questions? Comments? Jump in, guys, please. This is meant to be a discussion. Okay, so what have we just done? Here's the schematic thing. I have got my P and Q coordinates, and I've kind of zoomed in on the horizon. Here's the horizon, R is 2m. And what we've just done is we've created this patch of infalling stuff, which goes this way across this horizon. And the V patch goes into the infinite past. And I would suggest you, if you haven't, if you don't fully understand that, go and check and see that indeed the V is finite, corresponds to continuing T to minus infinity, and that R equals 2m in the finite values of V in this patch corresponds to T is minus infinity, and R equals 2m in this patch corresponds to T going to plus infinity. It's a very elementary exercise because all you have to do is look at what that logarithm is doing and the sign of the logarithm is doing. So that's what we've done so far. We've started here. We've done this square root branch cut thing, but now we've followed photons here and we've followed photons here. There seems to be a bit of a gap, and so that's sort of the next thing we have to talk a little bit about. There is a missing bit. And so to find the missing bit, you can do it in 3 different ways, all of which will amount to the same thing. You can follow space-like geodesics to the other region, perhaps going through the wormhole, or you can go to this future region and follow things, oops. Oh, what's it doing? You can follow things into the past or follow things from this patch into the future. And the cheapest and quickest way to do this, and this is the sort of way to motivate the Kruskal-Szekeres patch, is to basically do both the Eddington-Finkelstein patches at the same time. And that's what we're going to do. So what you do is you simply say, okay, I've got these 2 Eddington-Finkelstein coordinates, U and V, and I'm going to replace both R and T by U and V. And according to, and basically from this, you see that one is just the sum and the other one is basically this tortoise coordinate difference. And basically you now write the metric in terms of both. So if you write the metric entirely in terms of U and V, this is the metric. And R, that R there, is now implicitly defined in terms of the difference of U and V. Okay, so it looks good, except for one thing, you've screwed it up. This metric is singular at R is 2m. And so you've got to fix that. And this is what Kruskal-Szekeres essentially did. So the problem is that the metric is degenerate at R is 2m. It has the inverse is singular. But if you look at this formula, basically you see that if you look at R is 2m, then this log diverges and it goes to minus infinity. And so you can, what is happening is that this R is 2m has now been moved to U is minus infinity or V is plus infinity. So the horizon sits at some infinite value of U or V. And so the trick is to bring it to a finite point. So R equals 2m is basically accessible with geodesic finite proper distance. I'm not going to go there. So the standard way you do this is you simply say, okay, if I want to bring minus infinity to a finite point, let me define a capital U by taking its exponential. And if I want to take plus infinity to a finite point, I just exponentiate the other guy. So you do that. And it puts U as minus infinity and V as plus infinity at a finite point. And then I'm going to flip around things again, flipping these capital U's and V's to get a more canonical form, which is what I'll call capital R and T. And you'll see that basically R is going like, some function of R times cosh, and the other one's going like sinh. So what we've really got here is we've got Eddington-Finkelstein coordinates all over again. There's the cosh and the sinh, but some much more complicated function of R in front of the thing. And when you do that, you get the Kruskal-Szekeres form. And this is it. It's basically a null in terms of U and V, or I've written it entirely in terms of a standard Minkowski 2-dimensional flat space with a conformal factor and a sphere. Now, the point is that the radial coordinate is now no longer, if the coordinates are U and V or capital R and capital T, little r is defined implicitly. And so I'm going to relabel everything by turning it back to U and V again. I got sick of writing capital R and T. And so here's the summary. You make this rather complicated change of variables, U and V, which is basically Kruskal-Szekeres. This is like the X, and this is like the P and the Q that we had before, cosh and sinh, with complicated functions of R. And here is the metric in all its glory, the Kruskal-Szekeres patch. And the important point is it's absolutely smooth for all ranges of u and v, except when r is equal to 2, except when r is equal to 0. So that's the beast. And I want to just make a little comment that it's also one thing you have to check in this game is that you have little r is a smooth analytic function of the coordinates you've got u and v, and that's very easy. It's defined implicitly, but you can check that the gradient of this function is strictly positive, and therefore you find that the implicit function theorem tells you that r as a function of u and v is smooth and well-defined everywhere. Okay, so the whole point is that this metric is completely smooth for u and v from minus infinity to infinity, but with the restriction that r is bigger than 0. And that restriction that r is bigger than 0 is u squared minus v squared is bigger than or equal to or bigger than minus 1. R is 0 makes this minus 1. So the universe, the Kruskal-Szekeres patch, is u and v in R2 with the constraint u squared minus v squared is bigger than minus 1. So that's a lightning introduction to how you get to the Kruskal-Szekeres patch. Any questions or comments?
I have a small question.
Sure, please.
Why do we really go for this Kruskal metric? Because we already got a smooth metric with Eddington-Finkelstein, right?
No, okay, you have to, let me back it up a second. So the point is that the Eddington-Finkelstein doesn't give us everything. So the game you play in general relativity theory is geodesic completion. You say, can I follow every geodesic to an infinite value of its affine parameter in every direction? And I want to follow it. And one of two things have to happen. It has to go on forever, or it has to hit a real physical singularity. And so the real physical singularity is the singularity in the middle of the black hole. But this picture, we followed geodesics into the future across the horizon. We found this new patch. And we followed this region, this thing into the past. We found this new patch. And this picture makes clear there's a big gaping hole. And that big gaping hole comes from, if I sit at a point here and I look where photons come from, so I follow this into the past, or I sit here and I fire photons into the future, or I sit here and follow space-like geodesics, they all point to a second region. And so what we're doing at the moment is we're trying to combine this patch with this patch in such a way, what does this patch do? It gives us the future of this region. This patch gives us the past of this region. What we're missing is the future of this region or the past of that. So the goal is by combining both of these together, we should get everything, and that's what we're going to see. So let me just show you the picture, and then we will get where we there it is. So what we actually get is in fact exactly this region. So u squared and v squared is related to r by this, and the u squared minus v squared is minus 1 is the singularity. And there are two copies of it. There are two exterior regions, left and right. This is right one, left one. This is where we started. We followed things here. This is where we started and followed things to the past. Now we have, by combining everything, we find a completely beautiful coordinatization of this region.
Right. Okay. Thank you.
Did I answer your question?
Yeah, but this region 4 is not really so doesn't describe a normal black hole, right? We don't really need region 4.
Hold a sec. This is where we live. This is the space-time outside the black hole that we find in our universe.
Right.
And now this is the interior of the black hole that we see in the future. And
so
then
we
you can
don't
ask,
really need 4, right? I mean,
sorry?
it doesn't do we really need 4? What does it describe?
Okay, so you've opened up a huge and interesting collection of questions, and I'm not sure quite which way to go, but let me give you a general relativistic answer, and then we can open that up to discussion. I'm sure lots of people got useful things to say at this point. So we're doing a very formal game here. First and foremost, we're saying Schwarzschild is a vacuum solution to general relativity theory. And so what we're doing is saying, suppose that vacuum solution is true absolutely everywhere, except possibly for some delta function source sitting at the singularity. And it's vacuum entirely in the past and vacuum entirely in the future. And now we're saying, let's just follow all possible light rays, all possible particles in all possible directions within that game. It's a formal game because we know that this was not a vacuum for all time. There was a stuff that made the black hole in the first place, the matter. We're going to come to that in a few next. But there was the matter that made the black hole, and that's going to get into the way of all of this stuff. But we're going to continue the formal game. And we're going to say, okay, we're going to assume vacuum everywhere. We follow all particles in all possible directions. If we're living here, we have to go backwards in time to follow particles. But the physics question is, I'm sitting here, what things can influence me? And the answer is stuff from here, but also stuff from here. So therefore, if you're sitting inside this region, which is a perfectly normal piece of black hole, you can ask yourself, what's influencing me? And the answer is not just the stuff here, it's the stuff that's coming from here.
Right.
And similarly, so we absolutely need this region for some purposes. And other purposes, it will be utterly irrelevant. And I'll explain what those other purposes are in due course. So if you ask an honest physics question about this, you will get an honest physics answer. But the formal game we're playing here is that this is sometimes called the eternal black hole. It has been a black hole for all time in the past and the future, and it's a vacuum everywhere, except the singularity. It's a very formal thing. Samir or anybody, do you want to add something?
Yeah, I'd be happy to comment on this. It's very important people are focusing on this issue of the eternal black hole right now, because I think the whole reason that Malsina got led towards his direction, which has ended up with islands, actually has to do with this picture. Because what happens is that he actually started from this, and then on the two sides of this hole, he said, well, let's put a CFT on this side, a CFT on this side, because there are now two boundaries. And then if you look at the two CFTs, they have no Hamiltonian between them. They're not even touching each other. On the other hand, if you look at this particular metric, the bulk is all connected. One side is touching the other side. So it looks like if you have two CFTs which have no Hamiltonian between them, but they're entangled, it looks like the dual of that is something which is physically connected. So he started thinking that entanglement generates connections. So I think that is incorrect. And later when we come to this issue, we can discuss the physics. This is not the time to go into it, obviously. But I did write some papers where I showed that if you start with two different entangled CFTs, all you will get is two different entangled sets of fuzzballs. But it's just like entangling two different pieces of coal which are in two different places. You don't actually get a physical bridge between them. And if you do put the bridge, you will actually get contradictions. Again, you can only resolve them by non-locality. So the connection between non-locality, entanglement, and everything is starting right with this picture. And Malsina's paper of 2000 called Eternal Black Holes in Anti-De Sitter or something like that, I think is the actual root of where all this wormhole thing came from. So it's very important to understand this, but as maybe Nick will say a short while later, if you actually make a black hole from collapse, you would never get the other side because you can't, right? You start with only one infinity. You're not going to actually generate a whole new universe that easily. So,
actually, that's where you're going to go because those are your homework questions. So we have to put the matter in. But no, this is, you put your finger on a huge issue. And the short answer is the relevancy of this picture depends on the physics question you're trying to address. And but this, as Samir says, this picture, you have to understand this starting picture to understand an awful lot of other things that are going to follow.
Right.
So this is
Great.
Okay.
Thank you.
Well, thank you. Thanks for the comments and questions. Okay, so.
Nick, can I say something?
Please, absolutely.
I think it's important to mention that region 1 and 4 are not causally connected.
Yes. So the only way to go from 1 to 4 is basically through this neck, which is a space-like geodesic and space-like trajectory. So in this picture, time-like trajectories are vertical or within this 45-degree cone, and this connection is only space-like. The only way to go from marginally from region 1 to 4 is through a null geodesic or null geodesic that runs along this line. But it's an extremely formal thing because this is a perfectly timed photon fired from this universe in the infinite past, exactly aimed at this bridge and crossing into the future. It never gets into this space. It's trapped on the horizon. It's the frozen photon on the horizon. So it's a very, the only physical particle that can make it between 1 and 4 is something that's actually locked to the horizons. Anyway, thank you, Bogdan. Yeah. Okay, so what I want to do now is, again, the other thing that turns up here is lots and lots of Penrose diagrams. So I'm just going to give you a brief outline of the whole idea of Penrose diagrams, because this is close to the picture we want, but this is not quite the picture we always draw. So if you've not seen Penrose diagrams before, this is a really essential part of things. But any questions before we leave Kruskal-Szekeres? Because we're done with that. We'll come back to it once we've got Penrose diagrams sorted.
So Nick, I had a question about notation. So the Eddington-Finkelstein, you were using little u and little v for that, right?
Yeah, I think so.
And
yeah, and then I flipped it around.
You were using capital U and capital V in the handwritten part, which I think is conventional. But I think later on the slides, I also see again little u and little
v, and I've made v now time. Like I know it's I'm annoying, but okay, you know, that's what I did in my course. So v is actually a time-like coordinate, and u is a space-like coordinate.
Okay.
I'm sorry, I got tired of calling it capital R and capital T, which would be perhaps the natural things.
Okay, I understand now. Yeah,
and then I just relabeled everything U and V. I got tired of the fonts. Sorry. Indeed. So my notational thing. So Penrose diagrams, there's nothing mysterious about them, but let me just remind you of something extremely familiar, and then we're just going to do the same thing. Conformal compactification, you learned at complex analysis probably, it's standard game. What you do is you've got some flat space, R4, Rn, and if it's Euclidean, it's straightforward. You basically have what is called a one-point compactification, and what you do is you bring infinity to a finite point in the standard way by using the arctangent or the tangent function, so that theta is pi, basically at the north, theta is pi, yeah, theta is pi, maybe I've got my coordinates screwed up. Yeah, theta is pi. No, theta is whatever. I think I've got my, that should be theta on 2 or something. But anyway, basically rho goes to infinity. I'm sorry, I have, yeah, okay, I've screwed it up somewhere. Anyway, the point is it maps rho's infinity to theta is pi. Okay, so what you do is by making this coordinate change, you get a crazy warp factor, which is the cosine squared of theta. So this blows up like crazy, but you get the metric on a sphere, the n sphere. So in standard way of one-point compactification of Rn to a sphere, you simply use the arctangent function to bring infinity to a finite point, and then it maps it to a sphere. The whole point of a Penrose diagram is to do that in a Minkowski space. And there's a lot more structure. So you introduce null coordinates, because that's the new element, u and v, in the standard sort of way. And now you get the Minkowski metric and standard null coordinates. Nothing mysterious here. But then what you do is you start messing with compactifying these null coordinates. And it's worthwhile remembering that the u equals constant, v equals constant geodesics. Sorry, constant curves represent shells of ingoing, outgoing null geodesics. So do you do the same trick? You introduce capital U and capital V, which are the arctangents of these null coordinates. And then you start messing with the metric, calculating what du and dv are. And then you get, once again, this conformally compactified Minkowski metric. There's a conformal factor, which is now cosine of each of the null things. It was cosine of theta over 2 squared. Now it's the product of the two cosines. And you get this metric, which is essentially still, the sphere just goes along for the ride. And this looks a little mysterious. We're going to demystify it by rotating u and v to something that is not a null coordinate, but normal radial. So what we do is we flip the coordinates to what is effectively a radial coordinate and what is effectively a new time coordinate. And then you get this conformal compactification of flat Minkowski space. And the warp factor, or the conformal factor, is simply these cosines of these angles eta and chi. So we're going to talk about what this metric is and what it looks like and how you get the Penrose diagram out of this. So basically what you do, putting it all together, is here's the rather unintuitive changes of coordinates you do to go from ordinary Minkowski space to this conformally compactified Minkowski space. It looks unintuitive, but the way you get at it is simply what I said. You just take arctangents of the obvious null coordinates and plod along, and then rotate back to some more standard looking time and spatial coordinate. Now, the whole point is, what's the structure of this metric and what's the original patch? So the first thing is that since R is positive, you see that basically chi is going to be positive. That's what gives us the Minkowski patch. This will be important. And the other thing that also has to happen is for R to be positive is you want these linear combinations to be positive as well, which means that these arguments should be between minus pi and pi, or at least half. It should be much the arguments should be between minus pi on 2 and pi on 2. Or if you allow for the factor of 2, these lines in eta chi space will be all important. So t goes from minus infinity to infinity. It can do whatever the devil it likes, but r positive translates into this region where chi is greater than or equal to 0, and eta and chi live within these 45-degree lines. Okay, and the other thing to realize is that the three-dimensional spatial metric here is that of a sphere. Elementary fact, but basically you just do the standard Cartesians and the coordinates in R4, and you find that that's the metric on a sphere. So this conformal compactification metric is therefore smooth, completely smooth for 0 is less than chi is less than or equal to pi on 2, and it describes R cross S3. This is the S3, and this is the real line. So here's the picture. We're going to ignore all the spheres. They're going to go along for the ride for the moment. You have eta, which goes from, basically, I'm going to take it from minus pi to pi, but really it's chi is positive is all that matters. It's like the chi goes this direction, and then eta goes infinitely up and down. But the Minkowski patch is given by chi is positive, so it's going to be from here around to there, and in these 45-degree lines. So you draw it, and it's that. So the Minkowski, original Minkowski space is really this little slice drawn here. So now, if chi is not equal to 0, a point in this diagram, or pi, a point in this diagram has a big fat 2 sphere. Because if chi is not 0 or pi, this sphere is sitting there and it doesn't have 0 size. But when chi is 0 or chi is pi, this sign vanishes and it collapses to a point, the north or south pole of your sphere. So the structure of this diagram is that when chi is 0 or pi, you really have a genuine point, but everywhere else you have a non-trivial 2 sphere. So what you do is you take this picture and you unpeel it. And this is the standard conformally compactified Minkowski wedge. And these are the 45-degree lines that define the essentially conformal infinity. And the surfaces of t is constant, r is constant, are these basically hyperbolic sections that I've drawn in this way. Okay, now there are certain pieces, geographical features, for want of a better term, to this diagram. There's this point up here called future time-like infinity, and it is this point here. And basically it is at infinite time, and it's at chi equals 0. It is a point because it's at chi is 0. Similarly, there's past time-like infinity. The other point over here is actually space-like infinity, and basically you see that what's happening here is that time-like curves all run up into I plus, starting from I minus, and space-like surfaces all end on I naught. Then there are the null structure, usually called scri plus and scri minus, and these are these 45-degree lines defined with strict inequalities here, and they are basically the topology. They're all S2s times the real line between here and here. So that's the structure of infinity in a Minkowski space. And all Penrose diagrams do is just use this fact for anything that's asymptotically flat. So Penrose diagram basically is a very cool, cute way of representing your space-time. It's always basically two-dimensional, except of all these funny little points, I naught, I plus, and I minus. It's basically, everything is essentially a topological 2-sphere at any point in the diagram. Basically, anything that's at 45 degrees in this picture is to be considered a null curve or null geodesic. And so lines at 45 degrees, we try and draw the diagram so that they are precisely null geodesics. And the physical original manifold is the interior of the diagram, and these are formal boundary points used for discussing boundary values of fields. Okay, so asymptotic flatness in a nutshell is this picture. You know, if it's asymptotically flat, it has to connect onto the asymptotically infinite structure of this diagram, and all you're going to do is glue in a new geometry, whatever it is that you're interested in. So if you do it for the Kruskal-Szekeres patch of the black hole, all you're going to do is map this flat region and this flat region to something which is essentially the standard eternal black hole. And so you have an asymptotically flat region here, you have an asymptotically flat region here, you have two copies of everybody. I've conformally mapped the singularity from this surface to a nice straight line. And every line in this diagram that runs at 45 degrees is a null geodesic, and I've given the formal definitions of the horizon structure here, but I'm not going to bother with this. So that's the Minkowski. So that's the Penrose diagram of the eternal black hole. And so the important point here, this is to really answer Samir's question, is to note that in this thing, in this Kruskal-Szekeres patch, there is this beautiful piece of flat two-dimensional Minkowski space. And that's what leads to the simple pattern. Oh, I guess I duplicated myself. All right. Now, that's the end of that. We're going to talk about putting matter in there, but I've answered, I think, the next of Samir's questions of what does the Penrose diagram look like for an eternal black hole? Any questions or comments?
There was a question for you in the chat.
Yeah,
Oh, I didn't see. Sorry,
yeah, it's actually the same. It's that was me.
Sorry, you're breaking up.
I'm trying to get through. Oh, sorry. Can you hear me now?
I can, but I think you need to speak slowly.
Okay. So I am trying to get an intuitive understanding of the Penrose diagrams, and I'm wondering if we can think of them as almost like phase diagrams. If we think of U and V as sort of, in Minkowski space, left going, right going photons, and in, black hole type of environment, ingoing, outgoing photons, then could we think of eta and psi as essentially capturing the phase between the two?
Maybe Andrea would give a better answer to me than I will, but I'm going to just simply say, no, really what you're doing is, you think of this as the Earth, and this is like the Mercator projection or some map. All you're doing is you've got a very nice, convenient representation of infinity at some finite point. And so it's a mathematical tool by which you can address the issue of what happens to a field as it approaches infinity in this space. Well, as you approach infinity, you can study the divergent structure much more easily on the sphere than perhaps you can on Rn. You encounter this when you discuss what's an analytic function at infinity. You map it to the Riemann sphere and you address the problem of the Riemann sphere, or perhaps you then invert through the origin of the Riemann, zeta equals 1 on the Riemann sphere. So it's a device for bringing infinity to a finite point so that you can really study it as a finite point in an extended manifold. The thing with Minkowski space is that the infinite structure in the extended manifold has a lot more structure than one point. It actually has 3 points: the time-like in the future, time-like in the past, and space-like. And it has null surfaces where radiation will leave. So if you want to address asymptotic behavior of fields, time-like fields wind up here and start here. Space-like fields basically go over here, and null fields leave here and come in here. So it's a way, the Minkowski structure of infinity is much more complicated than a Riemann sphere. And it's just simply a way of pulling that to a finite point, and then giving yourself a very nice, simple graphical representation by saying, look, for the purposes of most black holes or most stars, you don't really care about the sphere around the star. What you care about is the time and radial development. So you simply make a rule saying, look, I'm going to ignore the spheres, and I'm going to now just simply draw the picture where the spheres are points on this interior of this diagram, and I have this asymptotic structure, and I can address the behavior of fields as I go to there. But Andrea, I don't know whether you got something, because Andrea basically works on celestial spheres and things like this. Maybe there's another better answer to the question.
I think I missed part of the question before, but I mean, I agree with what you said, and maybe another point to mention is that the metric degenerates as you go to the boundary. And so if we think about, for example, the ADS-CFT correspondence, where we just have this nice time-like boundary, then we can think of the evolution of the boundary, which is supposed to be dual to what happens in the bulk, as starting from some space-like slice and then having some time evolution that takes us forward in time is much more, so you can use your usual quantum field theory intuition about what happens, because you just time evolve. While in Minkowski space, as you go to the boundary, the metric degenerates, and so you have a zero there, and then the question of how you can describe the bulk in terms of putative theory living on the boundary is much more intricate. and this d-dimensional bulk spacetime going to a d-1 dimensional boundary theory in de Sitter space seems to involve another dimension that gets lost on the way because of this degeneration of the metric at the boundary. So there's much more intricate stuff going on, and I don't think this is sort of fully understood. There's also a bit more complicated stuff happening around I0, but I mean, there's lots more complicated stuff going on in Minkowski space.
As Andrew is alluding to, there's a huge discussion about asymptotic, how the fields should behave asymptotically as they approach these surfaces. But the whole point of this process is to bring infinity to a finite point so that you can discuss what that point means or what this point means. And you can look at asymptotics of fields as they approach this point. The careful description of asymptotic flatness is a much more involved subject that mathematicians have worried about a lot. But if you're confused about, I know I'm moving fairly fast, these slides will be on the website that I sent around to everybody. I strongly encourage you, if you haven't seen this before, to work through it. I'm moving fairly fast, and in fact faster than I did in my graduate class, but I just wanted to give you the framework. And if you haven't done the homework, go and do it by working through the slides.
Maybe another point to mention is
ahead,
that the question of having a well-defined scattering processes is also something that has not sort of been completely understood over the last 50 years or so, since people think about, or maybe more, since people think about the correct boundary conditions of asymptotic flat space, how to describe scattering, gravitational waves, and so on. And there's a question of how because you here in these diagrams, you have a two-sphere at every point except at the special points. And you need to be able to say when stuff comes in from the past null infinity or past time-leg infinity, how it relates to the stuff that goes out at past or future null infinity or future time-leg infinity. Because at every point you have a two-sphere. And so the question is, do you have two different two-spheres of the future and the past, or are they connected? And so these are all questions that are only in sort of recent years, there's more discussion about it and an attempt to fully understand what's happening.
Okay, any other questions or comments? Or Samir, do you want to interpolate any comments at this point?
No, that's fine.
Okay, good. So what I wanted to do now is, what we've been drawing is this idealized picture. Where was it? Going back to, wait a minute, it was here. This idealized picture where we assume it's a vacuum everywhere. And then when you write its Penrose diagram, you just bring this into finite regions. Now we have to address, what about the matter that made the star in the first place? So the whole point is that if you draw it in sort of the coordinate patch, there is a star. This is the radial coordinate. This is time in the original coordinate patch. This is R is 2m. And basically there's some protostar that made a normal star and then started to collapse to a black hole. And basically, if you track the matter, it looks like this. And therefore, the corresponding conformal diagram just moves the singularity to here and brings infinity in. But this is basically the same picture drawn by hand rather than a pretty way. But this is the actual honest solution, honest Penrose diagram for a collapsing star. And you notice that we've lost region 3, we've lost region 4, and we've only got part of region 1 and 2. Well, we've got all of region 1, but most of region 1 and part of region 2. And that's because this is where it is no longer a vacuum. So this is the correct Penrose diagram for the collapsing star that makes this thing. And so we lose these extended regions. Okay, so we're almost to the last of Samir's exercises. Okay, questions or comments or concerns?
Nick, I had a comment.
Sure.
It's more of a technical question about doing these Penrose diagrams. You can also use hyperbolic coordinate? I mean, hyperbolic hyperbolic tangent, because
In what sense? Sorry,
so you can you have arctan, or you can use tangent, but it seems like can't you use like hyperbolic tangent?
You probably can. In fact, there's no one good way of doing it, but because you can always squish and deform the interior region any way you like. The one sort of basic golden rule is you want 45-degree lines to be null geodesics.
I see. So
so that tends to frame the thing for you. And so this process by which I deform the singularity to this is probably, I'm doing some clever conformal transformation on the side here, but you don't really care too much about squishing and mapping the spatial and time-like slices. So if you use an arctangent or use some other function, you can probably try it. I'm just following the standard route here that I learned when I was knee-high to a grasshopper, and you can do some other version of it. But the framing is always by the null structure.
Okay.
And that's part of the rules. 45-degree lines are null geodesics. And so that sets this, and sets the horizon. And that's pretty much what you've got. And the rest just squishes the shape of the curve. But remember, inside 45-degree cones, your time-like, and outside 45-degree cones, your space-like. So that pretty much means that this line has to be always less than 45 degrees. So technically, I should probably draw this close to 45 degrees because the collapse at the end stages is the matter is traveling pretty close to the speed of light.
Okay.
But yeah, I think you can do it with pretty much any function that brings infinity to a finite point will do it. So arctangents. Okay, go ahead. Say.
It's just more like an art form.
Yeah. Well, my art. Well, if I draw this takes time. This is easy. Okay. Any other questions or comments? So we've got these Penrose diagrams down. And now what we're going to do is talk about the slicing of them. And this is really getting to the nub of what Samir, I think, wants to get to. So here I've actually taken the time to draw out the Penrose diagram, extended Penrose diagram prettily. This is the exterior region. This is the second copy. This is the interior of the black hole. This is the interior of the path black hole. And because Samir, I think in one of his lectures or one of the references he gave, singled out the surface R equals M, as being a nice place to slice things, I've drawn it here. But remember, we're looking at space-like slices. We're looking at space-like hypersurface. That means they have time-like normals. And so outside the horizon, these are the canonical choices of T equals constant surface. And they basically are straight across here, or they bow upwards, or they bow downwards, but they never, ever tilt above 45 degrees. So the most extreme space-like surface at very late times is a hyperboloid that bends just inside here. And similarly bends such like here. But because R and T change from space-like to time-like inside, a space-like hypersurface is R equals a constant. Remember, R inside is a time-like coordinate. So basically, time is going this way, and decreasing R is the time. And T is now a beautiful space-like coordinate that maps out the surface. This is a point Samir was making much earlier. Every point on this is a sphere, which is kind of boring, but essentially the T, the time coordinates running this way, or the T coordinates running this way, and it's spatial. Okay, so the goal is to slice this thing with space-like surfaces. You want to study data for Cauchy problems, you want to do anything else, and the slicing that you want to find is what is called the good slicing. And a good slicing is one that stays the hell away from the singularity. And so a good way to do that is to slice at R is M, because the Kretschmann invariant, the Riemann squared, is nice and bounded and well, but reasonably tolerable at R is M. So we are never going to slice inside this surface. And so it's relatively easy to do a good slicing. So outside, you've got these T equals constant surfaces here and here. And basically, you start on these as you go to spatial infinity, and then you're going to get to the R equals M surface, staying away from the singularity, and basically exploit this surface to be the good slicing, because it stays away from infinity. And all you've got to do is figure out how to do the transition between here and here. And the only rule you need for this line is it never goes above 45 degrees. If it goes above 45 degrees, your surface has suddenly become time-like or null. So all I did was I just drew the obvious picture here and drew the obvious set of pictures here, where they start out as these hyperboloids that curl over, and then transition to this hyperboloid with a simple rule making my spline that I connected it with never go above 45 degrees. And so you see at very, very late times, you go up here, you cut across the horizon, and you can still stay on the R equals M surface, staying as far as you like, or not far as you like, R equals M away from the singularity. So that's the ninth problem. Samir, do you want to add anything more?
No, actually, that's a very nice depiction. It's a very beautiful depiction. I hadn't seen this way before, but I think it's a very clean way to see the slices.
Oh, I was doing my homework. I thought that's what you wanted.
No, I think in the single-sided black hole, they just look more ugly. I think in the two-sided black hole, you managed to show it very beautifully.
Well, I wanted to try, well, you know what the target is, of course, it's the island. So I thought, okay, let's just really make it obvious.
Yeah, this is good for the island, yeah.
So
I think it's probably also worth commenting that in order to achieve these nice slices, you basically have to stop time evolving inside the black hole. That is, you notice the ones that you've drawn, basically you haven't evolved the surface forward at all,
right,
as you go towards late time. And so this is not anybody's physical, spatial slicing, where you set up clocks and synchronize them, and rulers separating the clocks and so on. That
wait a minute, I think that's exactly what you're doing inside.
That's what you're doing, but basically the clocks, you stop the clocks from ticking inside R equals 2m.
Well, that's what I'm sort of synchronizing, saying, okay, indeed, I'm not allowing the interior. So R is the time coordinate inside. So R is M is saying, I am not letting anybody evolve nearer the singularity. In other words, beyond R is M. So the future is finite and it's at R is 0. And so I am absolutely freezing time at R is M. Yeah. But I'm absolutely freezing time just here too. I'm saying that this is T equals 15 billion years in the cosmology. And I'm freezing time across this surface, and I'm freezing time across this surface, and I'm then just joining up the dots.
Sure. But I guess my point is that, ordinarily, what is a physical coordinate system, physics coordinate system, as opposed to some mathematical coordinate system?
Okay.
It's that you set up some family of co-moving observers separated by proper distances, each one of which is carrying a synchronized clock. And you use that to, when the clocks hit, 5 o'clock at, spatial coordinate, XYZ, you put down a marker, you say that's a point in space-time.
Right.
And so, all experimental physics uses such, in the background, all experimental physics has such coordinate systems implicitly set up.
Right.
And all I'm saying is that what one is doing here is something which is a little bit unphysical from that perspective, which is that you declare that your coordinate systems will stop the clocks from running once they get inside R equals 2m.
Well, okay, I could simply, okay, I'm trying to understand the broader point you're making. I could imagine that I will allow you to run the clocks from R is 0.9m to 1.1m and just stay in that region and join up the dots so that these surfaces do evolve into the future. But I'm not going to let you go closer to the black hole than 0.9m.
Can I say something, Nick?
So hold on a second. I just want to hear the response to Emil's from that comment. So I'm not going to stop the clocks. I'll let the clocks evolve, and I'll join this to this at 1.1m, and I'll join this at m, and I'll join this at 0.9 or point.
But I guess what I'm saying is that if I have a black hole that's some particular size, and I'm carrying this clock with me, once I get inside the horizon, that clock has a finite number of ticks before it hits the singularity.
Absolutely, yes.
Okay, and so when you say I'm going to let the time asymptotically evolve according to asymptotic observers having an arbitrarily large number of ticks on their proper clocks,
right?
Then what you're doing is you're saying, I'm going to have a varying number of ticks on proper clocks along this spatial slice. And where as I evolve asymptotically, an arbitrarily large number of ticks goes by, where 3 ticks go by for observers who are sitting inside the horizon.
Yeah, okay, but I mean, if I were in a uniformly accelerating frame, or I were in some accelerating frame, wouldn't I have exactly the same experience? That observer would see fewer and fewer ticks going by compared to the guy who's out sitting back watching that. The number of ticks on a proper clock, this can become a huge differential for an accelerated observer, and I think that's just all we're seeing. I mean, what's happening is this guy here has got a huge number of ticks in their life, and this guy has got maybe a second, 10 to the minus 5 seconds for a solar mass black hole worth of ticks.
Yeah, but those sorts of things, those proper, those accelerated observers, those are the short shell coordinates that you were describing earlier,
right?
Where indeed a uniformly accelerated observer near the horizon, has a different proper clock experience to the asymptotic observer as well. But those coordinates never get inside the horizon.
I know, but the time differential, the tick time differential, is actually being set up here, because this guy, because it has an infinite number of ticks, but it's getting frozen down to a very, very limited number of ticks. In fact, the light crossing time of the black hole, which is this time scale here. So I think the differential you're alluding to is being set up precisely at the horizon.
To some extent, yes.
I think it's, it's the usual weird thing that when you get inside the black hole, instantaneous at the same time, you're at RS2m. This is or RS2m plus epsilon. This is a space-like hypersurface, and suddenly everything that ever fell into the black hole is on that surface with you. That's weird, but okay. Now you take that at face value and you evolve it forwards in time.
Well, the kind of thing you could worry about is, say, if your clocks are stopping, then implicitly your delta t from time slice to time slice is getting smaller and smaller. Therefore, you could worry that the delta e involved in specifying what's going on in those time slices is getting bigger and bigger.
Yes, I think that's true.
So do you run into, for instance, a high energy, a problem with using effective field theory because your delta E is getting arbitrarily large as you go to late times?
But isn't there a boost symmetry that you can apply to the boost transformer that you can apply to the double no coordinates, for example, that can move in between the different slices? So you can move this T const and R equal to M up and down the whole diagram, and then in that boost symmetry, I mean, your parameter will be the same for the whole slice. So actually, the time between the slices will be the same, whatever coordinate you're using.
Is that a question to me?
No, I'm just asking in general. Isn't there a boost symmetry in the space-time if you're writing double in the big U and V coordinates? Didn't Kruskal have some similar? That you can boost the coordinates in a similar way to the way Nick showed for the accelerating observer in Minkowski, that just leaves the metric invariant and it goes du dv, and then you can use that to boost the slice up and down.
There isn't quite a boost symmetry because the metric is still a function of R, and R is implicitly a function of U and V.
Okay.
Yeah. So, Samir, did you want to add anything to the discussion?
I wanted to add a comment, but somebody else I thought had a question.
Okay.
And maybe I'll just comment after that. Did somebody else have a question, or has it been asked?
Bogdan jumped in with a question. I asked him to wait for Emil to answer, and then, but I think Bogdan said what he wanted to say.
Yeah, so then I had a comment on what Emil was saying. Yes, that's indeed a valid question to ask, that if you slow time down on one side and not on the other, you don't have to stop it, as Nick was saying. You can just slow it down asymptotically so it never gets past something. But then you have slowed it down very much, on late slices. And does that create, let's say, virtual fluctuations if a clock is running slow? And do you have to worry about that? And actually, I did spend quite some time thinking about it, maybe a decade ago or something. And finally, I convinced myself that it does not lead to any physics effects for the following reason. I have a picture which I have drawn here on my iPad. If I hold it up, I'm wondering if people
can you just share? I can stop sharing.
Okay, I can share it.
Okay, I'll stop share.
Let's see if it picks it up. Okay, can people see this iPad screen?
Yep, you need to. Yeah, perfect.
So just take 1 plus 1 dimensional Minkowski space. And what I'm going to do is so this is 1 plus 1 Minkowski space. And I'm going to take my slicing, not the one which uniformly goes up like that. But, since I can use this kind of differential evolution, the first slice is down here. In the second one, I evolve it less on the left, but more on the right. Then the next one, even less on the left and more on the right. So a little bit like what I'm doing. Okay. I can't do this too much though. And that's the whole interesting part about the black hole. The reason I can't do it too much in Minkowski space is that after a while, this part will become 45 degrees. And then my slice will not be space-like. That's fine. I can do it for a little bit. So let me at least see the principles by doing this. Okay. The whole point about the black hole is I can do this arbitrarily because of the property of the metric. But if you don't have a horizon, you can still do it for a little while. And let me do that. So then the point is, suppose some interesting, because there are a lot of quantum fluctuations here because I'm not evolving very much. The small delta t means the large delta e. Maybe I even create some strings here. In that slicing, I'll see virtual fluctuations of strings. Maybe that's the kind of thing that Emil had in mind. At least that's the kind of thing I was worrying about. So then I tried to ask myself a question. If I have some virtual fluctuation of strings here, is it possible they reach over and do something to me here? For example, if I had a spin sitting over here, can these strings reach up, interact with it, and flip it down? Just making a toy question for myself. And I realized the answer is no. And the reason it's no is, even though I've done this crazy slicing, after this I can continue to relax the differential. So in the end, I end up exactly the way I would have ended up anyway. And because it doesn't matter which way I slice, if the spin was just going to sit there doing nothing, because I have nothing else in the space, it can't be that if I went through a crazy slicing in between and then came back to the old flat slice, that these virtual strings I created in my fluctuations, they can reach over and do something to me. So it is indeed true, if you ever look at some small time gap, like you make the delta E, delta t very small, the delta A will be very big, the wave function, all the fluctuations you will see, but those fluctuations don't do anything. And the way to see they don't do anything is that if they were actually going to do something, well, you just, instead of slowing it down from R up to R equal to M, for a little while, allow yourself to go up to R equals M by 2. You're still not near the singularity. They can't do anything because in this, now everything was smooth. So this Minkowski example sort of helped me to understand why there were no big effects from the slowdown. But it's an important question to understand because in the early days, when people look at a slowdown near the Schwarzschild horizon, they were seeing all kinds of virtual fluctuations because time had slowed down. And then Lenny was arguing the strings you see in the virtual fluctuations can allow information to reflect back from the black hole. But actually, none of that is true. As long as there's another coordinate system in which things are smooth, nothing will happen. That was my only comment.
Okay, I've got one last slide to show, which is the last of Samir's problems, which is sort of the money shot, so to speak. Oops, I'm sorry, stop showing you share. I seem to have hit the wrong button. All right, where's it gone? There it is. So can you see the good slicing slide?
Yes.
Good. Okay. So basically, so this is the way you can represent the good slicing, and essentially you stay away from the singular. The critical thing is to stay away from the singularity. And as Samir was remarking at the beginning, the volume, the space-like volume of this surface is actually infinite because t goes from -infinity to infinity across the surface, and there are spheres everywhere. So it's got a lot of space. The limited effect is this direction, which is now time. And it goes from 0 to 2m, and that's why, or 2m to 0, and that's why you die within the light crossing time of the black hole. But the last money shot is to go to the papers of on islands, and here is, I've just sliced out two pictures, the two that Samir directed us to. This is the picture of the island drawn in the in these sorts of Penrose diagrams. And what you're supposed to notice is the similarity between this good slicing and this picture. And here's another one. Here's the island again drawn in one of these conformal diagrams. And so the last of Samir's comments was to say, look, the island looks just like a good slicing. So I'm done. Over to you, Samir. Do you want to wrap it up? And also over to anybody who wants to ask questions.
Okay, so yeah, we'll let people ask questions on your nice slide. I mean, that was a lot of stuff you have in there. And then maybe I can just, after people have done asking questions, I could just conclude by saying a little bit about next week's problems, which I can send you later in the day.
That's good. But do you want to sort of summarize what the important conclusions were? You know, I tried to sort of set it up for do you want to add to something about the fact the island looks just like a good slicing?
So I think that's exactly maybe the summary. The island is nothing but the interior part of a good slice. And so sometimes people just get confused, like, what is this island? But it's very important to see that the island is just a good slice that Nick has presented, because then when you go to read the island papers, you will see that the calculation they do for the Hawking radiation is also identical to the old Hawking calculation. So the calculation is actually not different. And the answer is also not different. But I think because it is phrased in the new language of island and not just the inside part of the good slice, it sometimes looks different. So, so I think there's not much I wanted to add to that, but I think the punchline of what these slices are that Nick gave is the crucial thing. It is exactly just a good slice.
Okay, so questions, guys?
I wanted to thank Nick and Samir for a wonderful pedagogical subject. I think it's invaluable to the students. And I thought that I would share a toy with the kids. I'll put it in the chat. It's a website. I sort of draw these applets for people to play with black holes. Let me share my screen and show you. And the website is there. So this is falling into a black hole. You see, this is the observer. This is in the TR coordinates. Okay. You can play on the weekend with this. This actually solves the equations of evolution in real time from the TR perspective. And you can also switch to oops, I screwed it up. You can also switch to the other perspective if I do this thing right. And you can see how it takes a finite amount of time for the info. So if you get bored on the weekend, you want to imagine how it feels like to fall into a black hole, either in Kruskal or in the TR coordinates, play around with the applet. Thank you again for both of you.
Great. I've got this website that I use I put up for the ERC to keep them happy. I'll put all these links on the website along with my slides, because I know I went quite fast through the thing, but it is relatively standard GR stuff. But I urge you, if you didn't understand or were having difficulty with the presentation I was showing you, just go to the slides and go through them and send me an email if you get stuck. Questions or comments? Nobody?
I have probably a very naive question. So this island, whether it's still completely inside the event horizon or part of it is outside, how is it given that you will always be able to find a foliation of your spacetime where the island will be entirely within one foliation? Like that you'll be, how do we know that you can find a foliation where the island is not given slice of your foliation?
So that I think is obvious, right? Because island is just a space-like section. It's all space-like everywhere. And you can always take any space-like section out of the diagram and then just continue it in a space-like way to reach infinity, unless you hit a singularity somewhere. So when you saw it from Nick's pictures, the place where the island is in the Penrose diagram, there is no like time-like singularity blocking you, right? As long as there's no time-like singularity blocking you, and you're under the space-like singularities which come to the future, if somebody draws this and says, this is my island, now if you want to see it as part of a complete Cauchy slice, just continue it both ways to reach infinity on one side and r equal to 0 on the other. And then you can draw slices below it and above it. So you can absolutely do that. The fact of whether it is slightly, it ends inside the horizon or outside on the other side starts at r equal to 0, but whether it ends just inside or outside, that the island people talk about very often, it's not actually relevant to the information puzzle as such. So they also don't actually use that fact for anything. For some cases, they have it just inside the horizon. For some cases, they have it just outside the horizon. But the major entanglement they will be talking about later is actually between quanta which are deep inside and far outside. So exactly where that ends can affect at most, one quantum being either inside or outside. And that only contributes log 2 to the entanglement. The real large part of the entanglement is between all the large part of this slice that Nick pointed out, that slices as long as you want, depending on where you make it. That's the large number that people are talking about. So the fact of whether it ends exactly inside or exactly outside, I don't think has been relevant for anything in the island literature.
Okay.
Andrew's
Is it space-like by definition?
Sorry, finish up.
Is it space-like just by the definition of the whatever formula they're using to get it?
Yes, because they actually want to say they write a state on the island, right? So you can only give a state on a space-like piece, right?
Okay.
Island is a region. They're trying to write a state of something, and you wouldn't write a state on something which is time-like.
Okay, sure. Thank you.
Andrea wants to make a comment. Go ahead, Andrea.
Yeah, I mean, maybe this will come up in the next sort of sessions, but in these island calculations, are the nice slices always far away from the last nice slice, or did anybody try to, because I mean, even if you use nice slices, you might run into sort of funny results that you might misinterpret if you don't compare it to nice slicing in Minkowski space, as Samir showed before. Like, for example, because you have this accumulation of nice slices at the very end, like at the last slice, you could think that there could be some effects that are due to this accumulation, and unless you look at this in Minkowski space, where you can resolve the whole issue and there's a complete space-time without, where you would just use different slices that are equally good and don't give you this. So you could run into the contradiction that you get results that are actually not physical or can be explained away because you're using slices that end at some point. I'm just wondering in the computation in this islands computation whether anything ever happened like late, because at the end of the day you want the pH curve to go down until 0, and so how far are they actually taking this computation in showing that, and are the late nice slices is it ever important to use late nice slices, or maybe this will become clear in the next lectures? But
so I think, so it should become clear in the next homework that people do, because there we will actually be looking at the calculation of Hawking radiation. But the whole point is that what is late is that you try to make the right-hand side part of the slice, where the radiation is the outside part, you try to go as late as possible so that you collect more and more radiation. The inside part, you try to not evolve, as Nick was saying, because you don't want to go near the singularity. You can evolve it. And in the early days, most people did. They said, okay, let them fall into the singularity. But just to make it nicer and not have to worry about the fact of whether high curvature physics brings in some new effects, we prefer not to evolve it to the singularity. So we will be evolving the outside part and not the inside part.
Right, but so you could, I mean, it depends on the kind of question that you ask. But for example, if you ask, so that there was this, this following one work of Silverstein, who claimed that there could be sort of a firewall effect because of boosts near the horizon. But then you can use, so what I want to say is that if you use nice slices and you sort of pick your last nice slice, and you want to sort of study, for example, string production from d-branes that you throw into the black hole, then because of this accumulation of nice slices at the very late times, it might seem to you that you have a non-adiabatic production of strings. So that's an effect that you would not have expected because you have nice slices. You never go to the bad region, and you could resolve this in Minkowski space. And so I'm just wondering whether any of these sort of weird effects comes in the discussion of these island papers, or whether this is another issue that they don't even touch upon because their islands are sort of on nice slices that are still close to the horizon, and the discussion never even gets to that stage.
So no, they don't touch. The island people, as far as I know, have not been touching on that, partly because they're simply using JT gravity, which is just 1 + 1 dimensional ordinary gravity. So they don't actually have any new degrees of freedom like D0 branes or strings or something which could happen if you give them a large amount of energy. But the question is valid, and that's also what Emil was asking, I guess, a short while ago. That if you actually slow down evolution on one side and increase it on the other, that is a basic property of black holes, which is intimately connected to the fact that space and time interchange roles. And so it's intimately connected to the whole Hawking problem. And could it be that this leads to some effects? And so it was correct to explore that. You can explore whether it actually leads to some strings or something because you've slowed down the evolution and all that. And all I was saying was, I did look at the Silverstein paper also. I don't think it's correct. I mean, I think there are no effects, but it's very easy to get confused on that issue. And before that, even Lenny had papers like in the early 90s, where just looking at the Schwarzschild frame, he said, because time has slowed down, if delta t is small, delta E is big, I'll see stringy fluctuations. And that is true. Even in this room, if I look at a time interval 10 to the minus 41 seconds, I will see strings in this room. But that's true because even in nuclear physics, if you look at a nucleus for a very short time, you will see lots of C quarks because you're examining the vacuum over short times, you see lots of vacuum fluctuations. The question is, what does that do for you? And the point was, let's say in Lenny's case or in Eva's case, you have to actually probe a little bit more to see, does it do something for you? And the example that I was giving from Minkowski space, where I tried to do the same thing, showed me that actually you see effects which are apparently there, but later when you think more carefully, they are not there. And my exploring of the black hole led me to the same conclusion. That's all I was saying.
So, Samir, I want to pull you up on that because Emil had a follow-up comment that went into the chat, and I wanted to explore it a little bit further, which is your argument, of course, was because the Minkowski space has an infinite future, you can unravel this dilation, whereas the future of an observer inside a black hole is very finite, and therefore you can never unfold this time differential in the infinite future. And so your argument's not going to work for the interior state of a black hole, is it?
So for the black hole, I started again, that the Minkowski part was to help me get intuition of what I should do for the black hole. But when I went to the black hole, this is way back now, a couple of decades back, but I was doing exactly the kind of things that Silverstein was later trying to do in her paper. I said, okay, let there be a D0 brane on this slice. Let there be a D0 brane far out, let's say R equals 4m. If I slow this down, is there any chance a string can stretch from here to there and change the spin of that D brane? I tried to make models like this and look for the effects. And the reason that I found the effects were not coming is because, okay, if you stop to evolution at R equals m, it may look like, I mean, slow it down like exponentially at R equals m, it may look like a string can do something from here to here, and the spin of both the D branes will, let's say, exchange at that time. But what I could do is, I could do a slicing where instead of stopping at R equals m, at the point where I thought the spin of the inside D0 brane will flip, I could evolve it further to R equals m by 2. That's still not near the singularity, but I could do that, right? The moment I do that, I realize I haven't done, nothing is actually happening at R equals m, so the spin of this D0 brane can't actually flip at that time. So because you can't relax the whole thing, but because you can relax it at any given time, you can argue to yourself that nothing will actually happen. But you don't have to be convinced by that argument. It's very, very interesting to actually try to see model and effect. I have a D0 brane here, a D0 brane here, strings can stretch between them. Let's see if I have that effect will come. And you work with it for a while, and if you can get it to come, fantastic, you found a new effect. But I couldn't get it to come. And so I think it's not there. So that's the best which can be said.
Yeah, I have one last sort of comment, but it's probably foreshadowing things that are going to come up next time or future times. You know, for me, the thing that was sort of frustrating about the island is that this is the picture that I kept seeing, and this is the picture I learned at my master's knee eons ago. Where's it gone? This sort of thing. And I kept saying, okay, aren't you just telling us something, you know, the island people, aren't they just telling us something that we knew 40 years ago? That all the entanglement that winds up out here is actually in here, and you just found a cute new name for it called an island. And that's one of my primary issues with this whole subject. And I think that's where Samir is going to go. But did you want to make any comments about it now?
No, I think that's exactly the situation. But I think what we need to do is to disentangle that from all the other things which are in the island community, because somehow it's not very clear to everybody that the calculation they do with 2D gravity is the old calculation. The point is that what they do with it just sounds confusing, because then what they say with it is that, yes, it is the old calculation. The information hasn't come out in the semi-classical calculation. But even though we don't get the correct state here, because it's a semi-classical state and we don't believe it's the correct state, we will still make a density matrix out of that state, still within the same 2D gravity plus scalar field. And even though our state is wrong, we will argue that the density matrix we get from it is correct. And then we will do some tricks with that density matrix in evaluating it and argue that the page curve comes down. So the steps in this do not make any sense to me. If you accept the state, the information doesn't come out. They say the state is wrong. Then you say, okay, but then what are you going to do with it? You've done the old semi-classical and nothing has come out. So you're back to where you were as expected. They say, okay, the state is wrong. And so the density matrix we make by tracing this part out is also wrong, maybe. But when we compute it with our tricks using a saddle point, but the saddle point still uses the same 2D physics. So it can't actually have new physics. But when we compute using the saddle point, we'll get a page curve coming down. And actually, when you look at the calculation, you don't find a page curve coming down. Okay. So that's where the gap is. I mean, if you look at these papers, it's not easy to see why the page curve is, where is the page curve in it? And the point is, in a Euclidean calculation, there is no page curve. The page curve is a function of time. Euclidean calculation, time is periodic. There is no page curve in the Euclidean calculation. The calculations are actually Euclidean. The wormholes they talk about are saddle points in a Euclidean calculation. There is no page curve there. When they go back to the calculating the page curve, they start again from the picture that Nick just had on his slide, which is the actual Minkowski picture, which gives them the old answer where everything is entangled. And then they say the outside radiation and the inside island should be thought of as part of the same thing. And so it's not entangled with anything. So you ask, where do you get that intuition from? And then they go back to the Euclidean calculation and say, there they had a wormhole. But that wormhole actually did not actually give any information coming out. So somehow there's a circle in there, and we need to understand that circle. Right. So in my opinion, it's a circle. Okay, you have to also ask them what they think. So it's a circle.
I think we're getting ahead of ourselves. Did you want to spend? We should try and wrap it up after 2 hours. I think people just get fatigued. So can you spend a few minutes now just talking about the next homework set? And at some point, I'll start pinging people I know to lead the discussion for the next one.
Can I share screen again? Then maybe
yes,
I can.
Go ahead. Yes, go ahead.
Of course.
It says you've started sharing screen, Samir, but nothing's showing.
Yeah, it always takes some time to find it somehow.
Yeah. Okay. Good.
Okay. So I thought what I would like to post for the next homework, people just need to get a good physical intuition for what Hawking radiation is and who is entangled with who, because then we can come to our own conclusions about what the information paradox is. So the first thing I want everyone to be very clear about, I want the students to understand, is that everything we know for semi-classical physics and even string theory can be modeled by just quantum fields are modeled by point masses joined by springs. So I'm sure you've learned this in your quantum field theory classes, but I want everyone to review that masses joined by springs is a model for a scalar field phi of x. So this is x, and the vibrations of these things give you a scalar field. So the reason we want to do that is that everything you want to understand about Hawking radiation is just here. Once you have discretized all your scalar field into points and masses, the whole point is that if you start with a bunch of these points and masses and springs, let's put them on a circle. Okay, so it's periodic, just for convenience. And then suppose you stretch the circle. You start with all this coupled state of the harmonic oscillators in the vacuum state. That's the vacuum of quantum field theory. And then you, let's say, stretch them. So you put them further apart, which is like saying that the couplings are weakened, let's say, or any way you like. Let's suppose you stretch it. Then the state will no longer be the vacuum state, but will actually consist of having pairs of particles of the vacuum state. So that is actually all there is to the issue of particle creation in curved space. Once you understand that quantum field theory is just, masses joined with springs, then when you stretch the space, you see that there is actually going to be pair creation. And the whole important thing about the Hawking case is that now that you've learned about Eddington-Finkelstein coordinates, let me plot U here and R here. But roughly speaking, if you have a light ray which is trying to go out on the horizon, it stays on the horizon because it can't escape. If it's just outside the horizon, it can ultimately get out if it is trying to go outwards. If it's just inside, even if it's trying to go outside, it actually ultimately falls inside. So that's the whole thing that happens at a horizon. Something trying to fly outwards. If it's just outside, it flies out. If it's on the horizon, it stays stuck. If it's just inside, it falls in. So if you had these 3-point masses here joined by springs, let's say just 2-point masses, take one inside, one outside, and they're joined by a spring. Then as you go to later times, the spring gets stretched. So let's say the bond actually breaks. You have 2 coupled oscillators, and then you get 2 decoupled oscillators. So all the physics of Hawking radiation is right here, that there is stretching going on at the horizon. And so whatever we start in the ground state of harmonic oscillators becomes an excited state of harmonic oscillators. And the simplest model which actually captures everything, including all that you want to learn about entanglement, is to just start with these 2 harmonic oscillators and put them in a coupled state. So this is the calculation I would like you to do. 2 harmonic oscillators in a coupled between them. And then they are, you find their vacuum state. And then let's say at t equal to 0, you suddenly remove the coupling. You have 2 harmonic oscillators. Well, then you can write the whole thing in terms of the states of the first oscillator, so the state of the coupled oscillator. And now you are going to write it in terms of the states of the first oscillator. And you will find that when you write in terms of states of one times the state of the other, it's actually an entangled state. So it will look like 0 of the first times 0 of the second, plus a quantum on the first. So let me just write 1 times a quantum on the second, plus like 2 quanta on the first and 2 quanta on the second, and so on. Let's just drop that. Let's just take the thing, and you get the entanglement, and that's all there is to Hawking radiation. So once you have worked through these simple examples, you will have a feeling for where the particles are being created, why they are being created, and how they are entangled. Then hopefully you can do that fairly quickly, maybe in the first 2 weeks or 2 days of the week, because the last question I'm going to give you is the long one, where I encourage you to read through a paper. Maybe I will just ask you to read through the Giddings and Nelson paper. It's an old paper, but I think it has a complete clear calculation of the actual Hawking radiation in the Penrose diagram, showing all the wave packets and how they are entangled. This is also done in the notes, with my Gyan notes, which I keep referring to. So for a lot of these calculations also, if you look in the Gyan notes, they are there, but there are many typos there because they were meant for a course, but I was lecturing in person, so I never cleaned them up. So you can either look at the Giddings and Nelson paper, or you can look at my Gyan notes, but then you will actually have the full Hawking calculation with the entangled pairs in the actual context of the Penrose diagram. And then you are all set to actually, start talking about entanglement, small corrections, density matrices, and all after that. So this last thing will be big, because I'm actually asking you to read through a paper and work through a paper. But the other 3 steps, the first 3 problems, will just allow you to build intuition, which is all that you actually need after that. So is that good? Is that good enough for now?
Great, Samir. What was the other set of notes? Can you put that in the chat? You said your notes for something or other?
Yeah, actually, I gave the link in the previous write-up I sent you.
Oh, good. Okay, good.
There's a HTTP link. So this is some summer school I taught about 5 years ago in India somewhere.
Right.
But I never cleaned those notes, so there are many typos there. That's why I think it's better to read the paper.
Okay. So any other questions, guys? Any comments, concerns? The Giddings and Nelson paper, Samir, is that the one, quantum emission from 2-dimensional black holes?
Yeah, I'll send a link for that. Yeah,
I've just pulled it up on the archive, so I've got it here. That's Giddings and Nelson. So on the chat, there's the Giddings-Nelson reference. So any questions, guys? Any comments? Nobody wants to pick a fight?
I just wanted to say thanks for having this. It's going to be really useful.
That's good. I don't guarantee. Well, I don't know. The next one, we're going to need some volunteers to do the sort of lead through, and I might sort of try and pick a few names. I don't know quite what the best way to do that is, but I will start locally, postdocs. And then but seriously, guys, it would be great if you guys would jump in and ask questions. It's meant to be a discussion as much as I did a lot of talking. Samir did quite a bit of talking, but please feel free to jump in. Maybe today was relatively straightforward because it's basic GR, but really, I'll start doing what I did with my graduate class, which is assign at random at the beginning 3 people to ask questions in the next 1 hour. But it would be great to get the discussion going so that we can then. So look, this is a pretty tame audience. It would be great if you started giving people a hard time at the conference, which would be even better.
I think you can hear. Thanks a lot. Should I stop the YouTube?
Yeah, that's great.
Let's thank Samir again for.
Yeah, thank you.
And also to Nick, because he did the homework, so. Or something.